Alright, so in this video I'm going to follow on from a previous video I did on one-dimensional SUVAT equations, and I'm going to look at applying them in 2 dimensions. And once you can do that, then it's fairly simple to apply them in 3 dimensions, but let's stick with 2. So a reminder from something I brought up last video, remember you can only apply SUVAT type things to problems with constant or uniform acceleration. Another key thing for this one, when we start to move into more dimensions, is that forces or accelerations can't have an impact on velocity perpendicular to their direction. So I'll show you what I mean by that. So let's just draw in an object. So we've got, say, a ball here, and let's say it's travelling this direction here, and an acceleration is applied perpendicular to that. So you've got your acceleration, which is typically drawn with a double arrow. I'm going to say it's got acceleration A. Now what will happen is that the velocity will, if you think about it in 2 components, 2 different things will happen. One, the magnitude of velocity in this direction here will be completely unaffected by this acceleration. So if we say that's our J direction and that's our I direction, the component of v in the j direction will not change because of this acceleration, because it's perpendicular. But the component in the I direction will increase from initially 0 to a higher and higher value as time goes on. And that's an important property I'm going to be using towards the end of the video when I look at problems with directions. Okay, so those are 2 key things you need to remember. So let's have a look at an example of this with Ijk notation. So we've got a ball travelling with velocity 2i plus j, and it's subject to a uniform acceleration of I minus j. And you want to know what the velocity is, or the final velocity if you like, after 5 seconds. So we need to do this in the I and j direction separately, and then we can combine those 2 together to give the overall. So let's have a look in the I direction first of all. So we don't know what v is, so that's our unknown. We know u, if we look up here, u in the I direction is 2. We know that a in the I direction, is 1, because it's just I. We don't know the displacement, and if we look at the time, we know it's 5. So we don't know displacement, that's telling us we need to be using this old equation here. So if we plug the numbers in, so we've got u is 2 plus 1 times 5 gives you 7 meters per second, but that's in the I direction. Okay, so just pick these up before I scroll down. So we've got a component of 1 and minus 1. Okay, let's scroll down. So again, if we look in the j direction, is our unknown. U was 1, A was minus 1, S we don't know, and T was 5. So again, we're going to be using this equation here, exactly the same. So we've got 1, and then you're going to end up with plus minus 1 times 5, which gives you minus 4 meters per second. So just a word about what that minus 4 means. If we define the I and the j directions like this, if it has minus 4 meters per second in the j direction, that means we've got a component that way in the j direction if it's minus 4. And this is plus 7, so it's 4 that way, or in the j direction it's minus 4. And then it's also got the 7 there. So this gives you an overall, if we just scroll that up a little bit, means the velocity is going to be 7i minus 4j. And that gives you your overall look at the velocity after that time has elapsed. Okay, so that's that. So as always, I've got it nicely typed out if you can't read my handwriting too well. So that's in the I direction. Here we've got the j direction, and there we've got the overall taking into account both of the directions in one term, as we had in the question. Okay, so let's move on to something that's not IJK but uses column vectors instead. Very simple. Okay, so this one, we've got a car travelling velocity 2, 1, and it's subject to acceleration for 4 seconds such that it finishes with velocity of -1, 4. And it wants to know what the displacement is. So exactly the same type. The I term is like your top one, if you like, so I'm going to call that the I direction here. So V is -1, U is 2, A we don't know, S is our unknown, and T is 4. So if we don't know acceleration, that tells us we're going to be needing to use this bad boy right here. So let's put in some numbers. We've got U is 2, V is -1, 2 times by 4. So this term would be 1 over 2, so half times 4 gives you 2 meters. So that's the displacement in the I direction. If we scroll up a little bit, let me just memorize those numbers, 1 and 4. If we look in the J direction, we've got, that was 4, 1, A we don't know, it's our unknown, and T was 4. So using exactly the same equation, let's put in our number, so U is 1 plus 5, 4 even, sorry I was getting ahead of myself, 2 times by 4 gives you 5 over 2 times 4, which is 10 meters. So in terms of overall, you would express S as this, so it's 2 on the top line and 10 on the bottom line, like this. Okay, so let's have a look at that now, as usual. In the I direction, which I'm taking as the top line of those column vectors, as you can see, the IJK notation and the column vector notation mean exactly the same thing. There's nothing tricky here. And then we've got the J direction giving us the overall displacement of 210, just as I said. Okay, so let's ramp up the difficulty a little bit, because that's not too there. So most of these you'll actually see you're given magnitude and direction problems. So what will happen is you'll say it's got a velocity in this direction at a bearing or this or an angle of this. So the key with these questions is always trying to draw a diagram so you know exactly what you're looking at. Okay, so we've got a ball. Let's draw a ball. And it's travelling at 3 meters per second on a bearing of 030. Now remember, bearings are given to north. Let's draw our north line, and they're given clockwise of it. So that means we've got going 3 meters per second that way. Now, subject to a force on a bearing of 90 degrees, so that's perpendicular to that north line, causes it to accelerate at 2. So we've got an acceleration, which again we show with a double arrow, like this. And we know that this is 30 degrees. We know this is a right angle because it's 90 degrees. And it wants you to calculate the magnitude and direction of the displacement if the force is applied for 5 seconds. So the first thing with these is always to define our I and J direction. So I'm going to say this is our I direction and this is our J direction. Obviously I'm allowed to pick those directions, but I've picked it so one of them matches up with the acceleration or the force in this case, which is a fairly simple thing to do. Okay, so let's scroll that down so we can do some working. So in the I direction, let's see what we've got. So we've got U-A-S-T. Now, this is what we want to find out. our displacement t is 5, v we don't know, a in this direction is 2 cosine 90, and u in this direction is 3 cosine 30. Cosine of 90 is 0, so this a is 0 in that direction, which matches up with what I said before, that an acceleration perpendicular has no impact, so there should be no acceleration in that direction. Okay, so that's set that one up. If you don't know what I've been doing here, like where these cosines of 30 and cosines of 90 have come from, I suggest you go back and look at the video I made about resolving and calculating magnitudes. It's one of my earlier videos because it explains what I'm doing there. I'm not going to repeat myself over. Okay, so we've got those. So we don't know v, so we're going to be using this equation here. Like this, and because a is 0, we can forget about this term here, so it's just ut, so it's just going to be 3 cosine of 30 times by 5, which gives you 12.99 blah 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 meters. I'm not going to round it at this stage because I'm going to use it for calculating the magnitude in a second. Okay, so that's in the I direction. Let's keep hold of that. Okay, so let's look in the j direction. So again, v we don't know, u in this case will be 3 sine 30. Again, if you don't understand that, go back and watch the video. You know, it's 2 sine of 90, which is 2, and s is our unknown, and t again is 5. So let's plug this in. Unfortunately, we can't get rid of this second term this time, which would be nice, but we can't. So we've got 3 sine 30 times by 5 plus half times 2 times 25, or 5 squared. And if you put those into your calculator, you should come up with 32.50 blah 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 meters. But the question asks you to calculate the magnitude of the displacement and the direction, or in this case, because everything's been given as a bearing, you should give the direction as a bearing. So let's chuck those out of the way. It's a bit messy at the top of the screen, but anyway. So let's do the magnitude first of all. So we want to know s, we need to do the sum of the squares and then square root that. So because we don't have a k, we can forget about that. So that's the square root of, what's it, 12.99 blah 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 squared plus 32.50 blah 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 squared, which comes out at 35.0 meters to 3 significant figures. Now, because I'm not using this for anything later on, I'm not going to write our string of decimal places. And then let's think about direction. So let's form the a triangle so we can see what we're looking at. Oh yeah, sorry. So we've got it going at 32.5, but in that direction, arranging them tip to tail. 99 in that direction. That means the resultant is going in that direction. But remember, we want to give that angle there. So we've got two options here. The more eagle-eyed of you will spot that that angle is the same as that angle, so I could calculate that angle. I'm going to go a slightly more roundabout way of doing it, calculate this angle. So using your SOHCAHTOA rules, or whatever acronym you might have got, you know it's the opposite of the adjacent, so 12.99 with 32.50 blah blah blah. So we want to, that theta, gives you a theta value here of 21.786, blah blah blah, which means bearing is 90 minus that, which gives you 68 degrees, or because you normally give it as three numbers, 068 degrees there. Okay, so that's a slightly more complicated example using some resolving and combining. And just to re-emphasize that, if you didn't understand how the resolving or this combining was working, well worth your time going back and watching the video I've made about resolving and combining them together. But that is how you solve more complex problems.